Dr. Kishor Bharti is a senior scientist from the Agency for Science, Technology, and Research, or famous as A-STAR at Singapore. Dr. Kishor Bharti got a PhD in the Center for Quantum Technology in US National University of Singapore, and under supervision of Professor Quek. So if you remember, Professor Quek also visited us, I believe, probably 1 year ago or a couple of months ago. And Dr. Kishor Bharti is an expert in quantum error correction, quantum device certification, and computer quantum of cryptography. So welcome, Dr. Kishor Bharti, to the Research Center for Quantum Physics. I hope this meeting will be the start of the future collaboration. Thank you. So please, Dr. Kishor Bharti. Um, Hello, Dr. Kishor Bharti. I'm sorry. Oh, I think. Are you still mute? Yeah, we cannot hear your voice.
Can you hear me?
Yes, now we can hear you. Thank you.
Yeah. So let me do the screen sharing, and then yeah, I mean, if at any point, if there are any question or anything, like, please just stop me, and I will be happy to explain. Yeah. So just a moment.
Okay, so while waiting, so Dr. Kishor Bharti will present for 1 hour, and after that we can have a question session. So you can ask directly after 1 hour presentation, or you can type your question in the chat.
So can you see my slides?
Yeah, we can see your screen here.
Okay, sir. Okay.
Terus
Okay, perfect.
kecilin lagi.
Perfect. Yeah. Yeah. So as you can see, right, this is a talk on quantum machine learning, and I will try to give a overall summary of the field, like what is quantum machine learning, and what's hard there, and what is next, what's happening at the moment, and this is more of an invitation for people to join this research field and contribute to it. So you might already see that, like, I mean, yeah. So these are the two organizations that I'm affiliated with currently at in A-STAR. So one is Institute of High Performance Computing, and the other is Quantum Innovation Center. And and um, and basically, many of you might have seen this 2x2 diagram, where, like, you have type of algorithm and a type of data, and the algorithm can be classical or quantum, or data can be classical or quantum, and depending on that, you have, like, 4 different quadrants. So normally when people talk about quantum machine learning, they can mean any of these three, like any place where quantum is involved, they talk about, quantum machine learning. And this part is basically classical machine learning, that both data and the algorithm, they are classical. So this is classical machine learning. But yeah, you have 3 other quadrant. This is like genuine quantum machine learning, like everything is quantum. But you could have also, let's say, data which is classical, and you are trying to use a quantum processor to learn, do something interesting. So that part, like also people can like and explore. I mean, am I audible to everyone? Like, I mean, or is there an issue with my voice? Like, I mean, can people hear me?
Yes, I can hear you loud and clear. Thank you.
Okay, perfect, perfect. Yeah. Also, there was recently a very nice paper from the Google Quantum AI team, where with DeepMind they used physics and quantum physics and AI ideas to take care of like quantum errors. So this is something that is already being used to do something interesting. So for example, let's say to build better decoders and so on, which can be used in quantum computer, people have been using. So this has been like very much useful. So here I will talk about quantum machine learning, the overall idea of this field, and what do we have and where do we expect to go and so on. Yeah. So currently we are in this regime of noisy intermediate scale quantum devices. So we have these devices which are noisy, like there is some noise, and the noise is, let's say, like some constant noise, see, like per gate component. And on top of that, there is this thing called intermediate scale. So like we have, I don't know, maximum, let's say, 1,000 qubits, and in this kind of this noisy intermediate scale setup, people have been trying to like do something interesting, which is classically can be challenging, such as this like this experiment by Google, like this experiment by Xanadu. There was experiment by the Chinese team in USTC and so on. And there is a hope that like we can do something interesting with these devices. And these devices have like led to, I would say, a kind of a hope, where like all over the world you see that there are so many companies that are being created, and like as you can see, like I mean, not only in Europe and North America, but also in Asia. Like there are several companies. Like for example, in Singapore, we have like uh, yeah, like a few companies working in quantum computing and so on. So there is this constantly growth of I would say quantum computing. And you can see that like IBM, for example, also had this kind of a roadmap where they talk about how their number of qubits will increase over time and so on. I don't know, maybe they revised it, but like I mean, this has been one of the roadmaps. So so in this era where like I mean, we are in this noisy intermediate scale quantum era, there is a goal to like do some quantum computing with the devices and see whether like we can get anything interesting. And John Prescale, like whose picture you can see here, in the past, he explored this, and he said quantum computing in the NISQ era and beyond, and he wrote a very nice paper on that. And following this, lot of work has been done, and at some point, like we reviewed it in as part of this paper called Noisy Intermediate Scale Quantum Algorithms, where we summarized, and as part of that, we also talk about like quantum machine learning there. So if somebody is interested in quantum machine learning for, let's say, near term quantum devices, like I mean, you can potentially have a look there. So, so let's say, even if we go into like what is a quantum machine learning, I think one thing that we should try to make sense of is what is machine learning. Like I mean, or so machine learning is a subset of like a big um, uh, like area called artificial intelligence. And a subset of artificial intelligence is machine learning, and a subset of that is like deep learning, when you work with like neural network, which are like not shallow, so they are called deep learning. So you have this three areas, like DL, ML, and AI. So AI is the at the top, and then ML, and then DL. And there can be many different definitions of AI and so on that like people can talk about. And like and one of the approach to solve the AI problem, like building such device problem, is allowing the machines to learn from experience. One of the approach to solve the AI problem is by allowing the machines to learn from experience. This is very important, by allowing the machines to learn from experience. And this is what is called machine learning. So you can see there is a nice survey at some point we did with like Quake and others, where like we looked at how quantum foundations and machine learning, they are benefiting from each other. So like you can see a bit there, yeah. So when we talk about like machine learning, one of the things is like what exactly does that mean? Like, I mean, obviously, like there is some like experience that you are trying to convert into expertise, but how do we make sense of this? And Tom Michel in 1997, he basically says machine learning is something where a computer program is said to learn from experience E with respect to some class of task T and performance P if its performance at task in T as measured by P improves with E. So much complicated wording, but what it means that you measure performance for some task T, and as E increases, the experience increases, this performance increases. So performance should increase with experience for some task T. This is what it simply means. I mean, this it makes sense, right? Let's say you have some candidate, you hire them, and their experience is increasing with time, but their performance is going down. So let's say if this thing is going up, this thing is going down, then you will say that like you are not learning. So learning very much means this thing, like the performance should increase with experience at some task T. Effectively speaking, learning program is something that takes experience and converts it into an expertise. So that's what a learning program is. And there are several examples, like spam filters and so on, where, like you try to find the difference between what is a spam and what is not a spam and so on. Yeah. Also, there is this very nice like example of, let's say, rats. Like there's this experience. Sorry, there's this experiment where, let's say, if you try to poison rats, it's very difficult to poison them. So basically, what they have is something called bed shyness. Like and they use inherently some machine learning kind of behavior to protect themselves from poison. So let's say if you give them some food, if it's a food which is like they have already seen, they will eat it, and they won't like care. But if it's a new kind of food, they will just eat just a little bit, and and let's say after eating that new food, they get sick. The other rats will observe them, and all of them will stop eating that kind of a new food. So it's very difficult to like put a bait to rats, because like based on some small data, they often generalize and make sense of things. In some cases, like this kind of learning is not really true learning. For example, like it can lead to something called superstition also. So it's some kind of a bias, which is also a much one can think of, it's learning, but like it's learning with bias. Yeah. So this behavior not only is seen in animals, sorry, humans, where like a human sometimes believe in some extraterrestrial entity or something, and in the absence of evidence, like it's also is believed, like for example, pigeons. Like, so you can see superstition behavior in pigeon also. So BF Skinner, he has a very nice textbook talking about it. So if you think about it, it's basically we also do learning. We also like develop experience to expertise, and effectively like we are also like machine learning, if we can say. So classical machine learning has, like progressed a lot, and you can see that there has been, like papers where, like people have even put Chat GPT as co-authors. So using Chat GPT, like they are trying to do some interesting stuff and so on. And DALE, for example, is being used to generate pictures and so on. But let's say these are all like practical side. Even on the theory side, if you were like interested in this, there's a very nice textbook by Shai Ben David and Sai Schwartz. And on YouTube, you can see very nice lectures by Shai Ben David on machine learning. So that can be very good. Like if someone is interested in machine learning and wants to, like understand what learning means and so on. So very nice textbook here. Yeah. So at this point, if anyone has a question, like please just stop and ask me, or like I will just move to the quantum part. So this was like the classical, the motivation and the classical part. I will now proceed with like the the quantum part here. Okay. So so in the quantum world, things can change many ways. So for example, your algorithm like earlier was using some classical circuit. So earlier you could have algorithm could use like classical circuit, but now it can be a quantum circuit. Like that's how you can change things. Similarly, data earlier it was classical, now it can be quantum. Now, so depending on that, you have like you have like here the classical ML, but you can have QML, QML, anything where like at least there is one Q, you get QML, and this is like genuine QML, where like the data as well as uh, algorithm both are quantum. Yeah, and it's genuine quantum machine learning. So there are three quantum machine learning approaches that we are aware of. I mean like that, like one can categorize. One is those algorithms which has been designed for like very far away devices. So let's say assuming in future we have a quantum computer which have very small amount of noise, they are reliable, they can run circuits which are like very large. Basically what it means that polynomially depth circuits, the corresponding quantum machine learning algorithms are called fault tolerant QML algorithms, and this is a very nice survey where people talk about it. For in the noisy setup, you can like you can discuss this thing called noisy QML algorithms, and you can discuss it here. You can find it here. There is also like a statistical side where from a statistical learning theory perspective, people look at, like QML, and that's quantum learning theory, which is, by Srinivasan and De Wolf have surveyed this thing here. Yeah. So you can look at, like these three references. After this, like many new references have come, which I will mention towards the end. But yeah, like, these have been some of the initial references. So let's say when we are talking about, like, QML, the first thing that comes to mind is like, what is data? Like, you need to, like think about data, and then you need to put that data on the computer. So let's say if the data is, like, let's say classical, what you can do is that you can do something called basis encoding. So you can put the information in the basis register, like, basis of your quantum registers, and that's like basis encoding. You can also put it in the angles, and that's called angle encoding. You can put it in the amplitudes, and that's called amplitude encoding. So, like there are a few of these things. In some cases, like, it's completely quantum data, and it could come as, like some quantum state or process, or it can be description of some Hamiltonian or like something like classical shadow or something. And, like these are some examples of data which is, like quantum, and that can be represented in some interesting manner. So there are many examples of data where, like data that can be generated or simulated on the quantum device. And, like, from Google TensorFlow, like quantum TensorFlow, you can find such several examples of data that is, like genuinely quantum. So like it's in something in as a output of classic chemical simulation, quantum matter simulation, quantum metrology, control, communication networks. In many cases, like data is genuinely quantum. So when you are trying to solve, let's say, a linear, machine learning problem, the first thing that comes to mind is curve fitting. Like basically, it's effectively, some curve fitting, where based on some data points you fit a curve, and then for new data points you basically predict, like given a value of X, give me the value of Y. Given a picture, tell me whether it's a cat or a dog. And the curve fitting that we do, that can involve like complicated like curve fitting for large like degree polynomial. But the simplest example of curve fitting that many of us might have seen is this thing called linear regression. which works for, like linear system. So some of the early examples of machine learning that many of we do is this, like a linear fit. And even in the quantum case, it's the linear system problem. The once people developed the algorithm for that, that led to the birth of quantum machine learning. So it's important to discuss, the linear system problem. So what is a linear system problem? So in linear system problem, you have been given, ax equal to, like, it's like ax equal to b, where you have been given a and b, and your goal is to find x. So for example, it's like x1 plus x2 equal to 2, x1 plus 2x2 equal to 3. You can write this as a equal to 1, 1, 1, 2. This is A matrix, and this is B matrix. And the X matrix is not given to you. So you can write it like 1, 1, 1, 2, and then you have like, the X vector x1, x2, and that should give you, like 2, 3. So this is an equivalent way to write, like this statement here. So it's like x1 plus x2 equal to 2, and x1 plus 2x2 equal to 3. So you can write like this. So what you have here is this thing is your A, this thing is your B, and your goal is to find what is this X. Yeah. So you can solve this and you can get x1 equal to x2 equal to 1. Like for example, you can, yeah. So there are many methods through which you can solve it, and this is something that many of us we do in high school. But in quantum case, the things become a bit like challenging. Like first of all, this X is, is a ket, and this B is a ket. So, like you don't solve the same problem, but the quantum linear system problem is a modified version of this. It's like A ket X equal to ket B. So when sometimes people say that, quantum linear system problem, one has to be careful. They don't mean the same problem. It's a modified problem. So you cannot solve the original problem. So what often you do, if you can't solve a problem, you change the problem. And that's what, like happened here. The quantum linear system problem is like, modified version. And this was given by Harrow, Hasidim, and Lloyd in this famous PRL paper from 2009, which led to the birth of, like quantum machine learning. So often when you have access to A and B, what do you assume is that you have efficient access to B, and you can assume that, let's say you have been given unitary decomposition of A, like, A and B has been given to you. Often you assume that the number of such elements here that you have is order polylog n. Like that's what, like people assume. So the key idea in the linear system problem, so at some point we give an algorithm. So like this paper algorithm by Harrow, Hasidim, and Lloyd, that's a 4-term algorithm, and for fault tolerant devices, and that requires a lot of resources. So we don't know, like how to solve that in the near term, like, efficiently. And it's not possible in the near term. So what we do is that, we try to come with a near-term quantum algorithm. So with Robert Wong and Patrick Reventrost, we wrote this paper where we said that, like you can take the A and B matrices and use that to construct a Hamiltonian. And you could try to find the ground state of the Hamiltonian. And for any X, like, let's say that solves Ax equal to B, it will correspond to Hx equal to 0. So by finding the ground state of this Hamiltonian, you can solve this linear system problem. Once you have solved quantum linear system problem, it can have many different applications. So people have found this application in quantum principal component analysis, support vector machine, and so on. And there has been paper by Passcode, Lloyd, Masood Mosheni, and Patrick Reventrost, also support vector machine for data classification, and so on. But you have to be, like, as I mentioned in the beginning, you have to be very careful, like when people are claiming for some kind of a quantum advantage, let's say in general. Like there are details which one has to look. And Scott Aronson like very much mentioned this thing as read the fine print. And very nicely he talks about like what are some of the issues with like some of the quantum algorithms which are people talk for, let's say, machine learning. So for example, the A matrix that people talk about in it's assumed to be sparse. it's assumed to be, like its condition number has to be small, like the largest eigenvalue divided by smallest eigenvalue, that assumed to be small. Then on top of that, like you don't calculate the x vector, but you calculate, like x, m, x, like, this kind of object for some observable m. So there are details that one has to look at. And that's why, Scott Hansen says that read the fine print. Often, like myself also, when I'm in doubt and, like something, often it's a good idea to consult his blog, and he gives like honest opinion about what's going on and what are the issues and so on. And in fact, some of his worries like came true. And at that point, a teenager like Even Tong, basically, she wrote a paper where he said that quantum principal component analysis only achieves an exponential speed up because of the state preparation assumptions. So there are certain assumptions there because of that, like it, yeah. So she went on to dequantize many of the algorithms and so on. And the advantage that people thought of, that advantage was gone. But does that mean that, like there is no advantage? But in fact, like, what over time people worked, and under the assumption that, like some cryptographic ideas, people showed that, like indeed some kind of advantage is possible. And there is a very simple, like intuition for that coming from, like crypto. So let me like, explain that. Yeah, so using ideas from crypto, you can show that there exists some rigorous and robust quantum advantage for like many of the learning tasks. So the idea is very simple. You have, like you have the crypto, you have two kinds actually. You have like, you have a crypto world, and you have quantum, sorry, you have a machine learning world, ML. And there are two possibilities. Like crypto can be classical and ML can be classical. Crypto can be quantum and ML can be quantum. Now what happens that, let's say if you take, for example, factoring. So factoring is difficult, like, like it's hard to learn the factors. So factoring is, like hard, classically hard factoring. So let's say we take factoring is hard. But and that's why crypto people are very happy and they use it to give security. So ML people, like are very sad that they don't have algorithm for factoring, but then crypto people say, no, this is very good. We can use it for giving security. Happy. But then what happened in the quantum case, factoring becomes easy because of the Shor algorithm. So ML people are now happy, and then, like the crypto people are now sad. So you see that what happened, because what happens that, ML and crypto, they are quite opposite of each other. In machine learning, we try to find pattern. In crypto, we try to hide pattern. And often, let's say, if you believe that there are certain cryptographic problems which are hard, such as, let's say, discrete logarithm, or let's say factoring or something, under the assumption that these problems are classically hard, you see that ML cannot solve it if it's classical, but it can solve it if it's quantum. So there exists a separation between classical and quantum for certain problems, under the assumption that certain crypto problem is, like is hard, like in the classical world. And using this only, like, people gave like separations, and one can, like study this in detail. Also, like, using something called quantum memory, people managed to show, like some separation between learning bit and without quantum memory, like, yeah, exponential separation has been shown. Somebody could ask, like, can we like, do something interesting and, like, get advantage for some practical task, much more practical task. And people thought that maybe for topological data analysis, like there is something possible. So what happened that, like, I mean, in the beginning, like, there has been this craze for big data, and everybody said that, like, I mean, for big data, we can get advantage. And big data is good, like, I mean, maybe there's a lot of data, so people thought that, maybe quantum can process it very fast. but just uploading the data on quantum computer is challenging. So the right mantra is that, we don't want big data, we want small data, but big computing. So something that requires small amount of data, but lot of computing, maybe for that quantum can give advantage. And topological data analysis exactly fits there, where, like you have like small number of data points, but lot of computing you have to do, and so people thought, maybe one can do something interesting, and you see like, many paper written where one paper refuted another refuted another, and within a week, like, several papers were, like came on archive at the end, and so on. And it's not clear, like, whether we can get advantage or not, but in some cases, some special cases, it has been shown that like some advantage can be obtained for topological data analysis. So a very nice paper has been written by Seth Lloyd and these people here on complexity theoretic limitations of quantum algorithm for topological data analysis, which is worthwhile reading. Yeah. So that finishes, like the part where I may talked about, like the fault tolerant. I will now talk a bit about the NISC, and then maybe, like, yeah, like move towards the final part. Yeah. So at this point, if any question or something, maybe please ask, or I will move to the next part.
You can ask question.
Okay. So,
Crystal clear, I guess.
yeah, okay. So yeah, maybe I can, like, uh, yeah, proceed. So let's say now there is this part about, NISC algorithms. So so NISC, like, like fault tolerant quantum computers are many years away. Like, they're many years away, and we don't know when we will have that. Or yeah. So can we do something useful with quantum computers available now, like that we have right now? And there are several constraints with such computers, such as, limited qubit number, shallow circuits, noise, and so on. So the idea is to leverage quantum computers in combination with classical computers to do something useful, and that's what, like many people have been doing. And there is notion of quantum neural network, which has been, like, very much studied, where you have some parametric quantum circuit. So you're like, in the classical case, a neural network is just a parametric circuit whose parameters you can tune and learn whether, like it's a cat or a dog. In quantum case, it just becomes a quantum device, a quantum circuit. And that's what many people, like call that quantum neural network, like instead of, like a regular neural network. So you have some grades with parameter instead of, like a classical weights and biases that people put in neural networks. But there are several roadblocks, such as, like, often, like, the expectation value, like, the gradient of that, when you calculate, like it vanishes, and the variance, like decays exponentially. And because by using Chebyshev inequality, you can you can show that, like the gradient basically becomes zero, so it's a flat landscape, and you cannot get any used signal out of it. So this phenomenon is called barren plateau, and several work has been done on it. Like we have also something along this line. On top of that, the landscape is very non-convex. Like there are like many local optimas, and like, and this is bad. So that makes the training like NP hard, and there are like issues with critical points and so on. So the question somebody can ask, like, how to characterize the power of parameterized quantum circuit? Can we avoid barren plateaus and optimization and bad optimization landscape? Can be improved training of variational algorithms? Can be designed better classes of NISQ algorithm? And indeed, you can get an answer for this using quantum feature information metric and semi-definite programming, which we like on discuss in some of these papers, which I just mentioned here. So also, like, there is this issue with the noise, like, there is like lots of noise, and how can we handle the noise in the near term? And for that, something called error mitigation is very much used, and yeah, like people have worked on it. There's a nice review on it that you can refer to, and there are many error mitigation strategy that people talk about and so on. But then there are some fundamental limitations of quantum error mitigations. which like one should refer to in these papers. Also, these noisy quantum devices, they are bad with like optimization, and you can see that this paper where it says 7 that quantum and the bounds are or we often indicate that a substantial quantum advantage are unlikely for classical optimization unless noise rates are decreased by orders of magnitude or the topology of the problem matches that of the device. This is the case even if the number of available qubit increases substantially. So one has to look at. So obviously like the next obvious step is is a quantum error correction that like one so it seems that using error correction, maybe we can get rid of some of the noise. So we had this paper recently where we we say that can we do error correction in a much more simple and general way possible. So with Mile and Andrew Tangara, who is from Indonesia, we we wrote this paper here. Yeah. And then there has been, the final part, which I would like to just mention briefly, that there has been this approach where people are, approaching like this problem more from statistics point of view, and sorry, something happened. Oh, it seems my iPad crashed. Like the battery. Yeah, I should have been charging. Maybe let me, open it on my laptop and I share from that. Sorry about it. Just a moment. So I won't be able to like write on it, but yeah, hopefully this should this should work. Yeah. Okay. So okay. Yeah. So yeah, like there has been these approaches where you can also approach it more from the statistics point of view, and there has been like you can learn processes, or you can do a state tomography and so on, and there has been some nice works which discuss this, which you can read. Also, you can approach this problem more from a foundation point of view, where things like self-testing, state discrimination, or sensing, they can be also thought of learning task more from a statistical point of view. So one of the objectives in the near term is to demonstrate quantumness. So can be do something which is feasible on the current time devices. It's like the output is verifiable, and at the same time it's hard to spoof classically. And their existing approaches have some limitations. And one open question is, can ML task fit here? So that will be something very interesting, where if we can show that it's feasible on the current term devices, it's verifiable, and yeah, that will be nice. So it's important to find if we can find something here. Yeah. So we did some work along this direction, where we showed that random circuit sampling had some limitations. Yeah, that was also with Andrew. Yeah. Also we had some other work where we showed how you can prove quantumness using some other colleagues and so on. So yeah, there's lots of work, and I think it's a very much an active area of investigations, and there are many references here that you can refer to for lots of future work and so on. And I think that's it. Like that concludes my talk. You can look at some of these references, and if there are any questions, maybe please ask me, and I'm more than happy to chat and discuss. Yeah.
Thank you very much. Sorry, let me. Okay. Okay, thank you very much for the nice talk. Any question from the audience? Please raise your hand and you can ask directly. But I want to start with with one question. So this is very general question, man. What do you think will be happen in the next 5 to 10 years about state of the art of the quantum computing or the NISQ specifically? Next
Yeah,
5 to 10 years.
I mean, it's a very difficult question to answer. Like, I think there is potential, but you know, like, I mean, there is a lot of, I would say, challenges. Like the noise rate is very high at the moment, so one needs to do some error correction. And if we can have, you know, like a error corrected qubit, which can, you know, like let's say we can go up to distance. I don't know, maybe 20 or 25, maybe, or let's say like just 10. If we can implement that, uh, yeah, I mean, maybe what will happen that the noise rates will go down, and we will start seeing maybe some useful thing coming out of these quantum devices for I don't know, maybe for chemistry problem or something. Yeah. Yeah.
Some useful thing, hopefully.
Hopefully. Yeah.
Okay. Thank you. There is a question in the chat. What is classical shadow?
Classical shadow. Yeah, that's a very good question. So you can think of a classical shadow as something like, so you have some quantum state and you want to tomograph it and you want to know what is the quantum state that has been given to me. Now, what you can think of classical shadow as, like, let's say I have, you know, like some object, like let's say this thing. Now I can put some light on it. So then I get a shadow, right? Then I put a light in a different direction, I get a shadow. Then a light in one, then I get a shadow. You can think of measurements as putting a light. So you can put a light in random directions, like do measurements in random basis, and you can get different bit strings. Using this bit string, you can construct a classical description of the quantum object. That classical description of the quantum object, which is efficient, is called classical shadow. Yeah.
Thank you. That's another question from Abdurrahman. The question is, what is the current state of the quantum machine learning and how do you see state of the art of generative AI? Will it useful for QML or maybe QML will be useful for the generative AI?
I don't think, like, you know, I mean, I think these may be useful for, let's say, some problems in quantum. Like classical AI is very advanced, so they will be useful. But quantum machine learning, I think it will take some time. Like there are many challenges with training, noise, and so on. At the moment, it's a more of an exploratory area.
Okay.
Yeah.
Thank you. So it's still exploration.
Yeah.
Okay, so Agung, oh no, from Adri Sopiana, for QCNN, why is the accuracy of QCNN lower than CNN with the same architecture or layer?
I mean, first of all, there is all this barren plateau usage and so on. And second, the devices are very noisy. I mean, yeah, like you can say, like these are the challenges at the moment.
So the noise is the problem.
Yeah, noise is a big problem. Yeah. It's very noisy at the moment. Yeah.
Okay, so the noise, yeah. And then there's a question from Agung. How classical shadow is different from quantum state tomography?
Okay. Yeah. Hi, Agung. By the way, I know Agung for some time. Like, I mean, we met, I think 6-7 years ago, maybe. Like, yeah.
Hi.
So hope you are doing well. Yeah. Like,
How are you?
Yeah. Good. Yeah. So classical, I mean, quantum state tomography is like very, like, you know, resource intensive, right? I mean, it requires exponential resources, and it's like giving a complete description of the quantum state that works for, you know, like any observables and so on. But what you can have is that, you know, maybe you are interested in certain family of observables and not all observables. So what you at the end of the day we want is the expectation value of your quantum state for certain number of observables, and you don't want the actual quantum state, because what will you do? I mean, anyway you will do something with the classical output, right? I mean, the expectation value. So so the shadow quantum this classical shadow is I would say a more it's a tomography only, but it's more, I would say, a smarter tomography, where you say that, I don't need everything, I just need certain expectation values, and as long as I get that, I'm happy, and that reduces, the complexity of the problem. Yeah, like it makes it efficient. Yeah.
So you don't get the full density metric. You
Yeah,
only
don't
want
get the
to.
full.
Okay.
Yeah.
Mhm. Can I add? Can I ask another questions?
Yeah, sure.
Uh, is there at the present stage of the quantum machine learning, is there mathematical proof that shows that it is more powerful than this?
Using crypto. So that's why I'm explaining. So there's very
Okay.
nice paper by Srinivasan, Arunachalam, and so on, where they have shown that using under the assumption that discrete logarithm problem is hard, or let's say assuming that there exists certain one-way function, you can indeed show that there exists a separation between quantum and classical
Mhm.
machine learning. Yeah.
Even using the NIS, or I mean,
No.
are you
It's
referring to the full
it's fault tolerant.
fault tolerant? Okay.
Yeah. In this, I don't know. Yeah. Yeah.
Okay. Thank you.
Yeah.
Thank you. And next question from Dr. Khairul Anwar. Is it correct that the real problem in QML is finding the VQA?
That algorithm. Yeah, I mean, like sometimes it's one of the issue. Like, I mean, finding the right kind of, let's say, architecture, but it's not the only problem. Yeah, it's an important problem. Yeah.
Thank you. Two questions from Chung Pak Sen. The number one is how do you usually obtain quantum data? Number two, correct me if I'm wrong. From your presentation, it sounds like currently there is no definite advantage in quantum machine learning. Is this correct?
Yes, this is correct.
Okay.
Currently, there is no forget quantum machine learning. For any task, there is no definite quantum advantage at the moment. Nobody has any quantum advantage for any task currently. Yeah. And
Very
quantum machine
straightforward
learning.
answer.
Yeah. Like for no task, and in near future for some time we won't have. But yeah, like I mean, but if you talk to companies, they can say a different story. But the truth is there is no quantum advantage. Nobody has quantum advantage. And the thing is that how do you usually obtain quantum data? You can think of, it's output of some quantum experiment. Imagine in a large hadron collider, you have like an atom, they collide. It's some quantum data coming out. Some quantum a chemical reaction. In the output of the chemical reaction is quantum data. So many of the cases, like you can get the quantum data. Yeah.
Thank you. Wonderful for the straight and honest answer. That's correct. Yeah. Okay, so we still have a lot of time. Please raise your hand if you want to ask question, or you can you can write your question in the chat. Okay, well, it seems that, okay, there is a question from Cessnan Ledito. How useful is error mitigation in addressing barren plateau issue?
Yeah, so I mean, there is this noise-induced barren plateau. I'm not sure if it can, because how much noise it can be suppressed by error mitigation such that, like you can handle it. It could be useful, but I'm not very aware of, like, I mean, obviously error correction can take care of a noise-induced barren plateau, because the noise will be, can be exponentially suppressed. But error mitigation will only like try to get the noises expectation value, and I don't know like how much you can get rid of the. Yeah, people might have studied, but I think I'm not very aware of this. I mean, thanks. This is a good question. Yeah.
This one question from Gagus. Can you elaborate more on why the Fisher metric can solve or reduce the problem of barren plateau?
Yeah, like you can look at rank of the quantum Fisher information metric, and that can tell you how many parameters are needed in your parametric quantum circuit. So let's say if you are more than that, then you are in the over parameterized regime. Less than that, under parameterized regime, and so on. And using this quantum Fisher information, you can basically diagnose the landscape and basically use optimum number of parameters. So in this way, it makes basically like task easy, and gets help, like not like gets rid of the barren plateau problem, but helps you with the barren plateau problem. Yeah.
Oh, Agung asks again, can you explain the idea of self-testing?
Yeah. So self-testing is, I mean, as the name says, it's self-testing, right? You test itself. But technically, mathematically speaking, what it says that, imagine I have this phone. Somebody claims that it's an iPhone. But what if this phone is actually a Samsung phone, and it just looks like like iPhone. What if inside is like all the components are from Samsung, and the company is just cheating me by giving me bad phone? So can I test it? So maybe I can, the best is that I just open it and I check what is inside. The other thing is that I press buttons and look for like some behavior, and from there I try to know like whether it's an actual phone, or whether like it's like, I mean, fake phone, like it's a Samsung. I mean, Samsung is not fake, but I mean, in this case, I mean, like, yeah. Now um what this self-testing says that just by looking at the statistics, you should be able to tell what is going on inside the device. So this is something that happens in the case of Bell scenario, like in Bell non-locality. Like the moment you reach, like let's say you put the buttons, and let's say you get 2 root 2. The moment you get 2 root 2, you know that Alice and Bob, they must be performing, like those measurements which are XZ and the rotated X and rotated Z on maximally entangled state up to some irrelevant local degree of freedom. So this is like the notion of self-testing, and which has been initially given for like, maximally entangled state has been, like generated for, like many more like, family of states and settings and so on. And it is called self-testing because, you are not opening the device, you are just, like pressing some buttons and you are telling what is going on inside. So this is very much very quantum behavior. Like in classical case, yeah, I mean, I think it's difficult to tell, right? I mean, what's inside normally. Yeah.
So this idea is related to the device independent.
Yeah, exactly.
In quantum
Exactly.
cryptography.
Yeah, exactly.
Mhm.
Yeah. So
Thank you.
you can think of all of this as related to learning, in the sense that you are learning what is inside the device by just pressing a small number of buttons. Yeah.
Mhm.
Yeah.
Thanks.
Yeah.
Thank you. As a question, what field that contribute to the advance of QML most? I think he asked whether is it physics, computer science, or mathematics.
I mean, all. Yeah. I mean, I can say one. Yeah. All. Yeah. I mean, mathematics helps, like, computer science helps also. Physics ideas are also very much important. Yeah.
Okay. We still have time. Please raise your hand if you want to ask question, or write in the chat. Okay. Other than cryptography application, is there any proof that QML outperforms CML, especially for quantum computing in chemistry problem, like ground state energy of molecule?
Yeah, I think, like using something called quantum memory. So if you can have quantum memory, people have like, shown that you can do some interesting things. So for example, let's say if you can store the quantum states and you can do some processing on it, in that cases also you can do some. So I think there is a paper by Robert Huang, Jordan Kotler or something, where they have shown that you can get advantage. Yeah, if you have quantum memory. And you can intuitively see it, right? I mean, like, you know that, let's say, if you try to measure, for example, purity. So purity involves, like trace rho square. And rho square, if you want to measure out of some density matrix rho, you need to measure many copies. On the other hand, if you have memory, quantum memory, then you can take 2 copies of a rho and then apply just a swap on it. So it becomes trace of V rho tensor rho, which is, trace of a rho square. So just using 2 copies in a memory and performing swap on that, you are able to get trace rho square, which otherwise will require, exponentially many copies. So yeah, I mean, having quantum memory can help. Yeah. And I think with chemistry experiments and so on, I think it will become very useful there. Yeah. Because you are interested in these things like purity and so on there, right? Yeah. Or some properties which are non-linear function of density matrices.
Thank you. You have more question? Oh, what are the key and the indicator of quantum advantage in QML?
Key indicators of quantum advantage in QML. Yeah, I mean, if you, let's say, the best thing is that, I have a problem. Can you solve it faster? Like, let's say, cat dog recognition. Can it, I mean, so obviously, like, there are things like time complexity, space complexity. Like, using complexity theory, you can talk about advantage. Like, if some problem has on quantum computer a smaller complexity that on classical computer, then you can say it helps. Other thing is maybe accuracy. Like, in accuracy, you can get advantage. Maybe you can solve it faster, but is it accurate? Like, what is the amount of error? Like, in one versus another. So that's another error, like example where you can, I mean, it's a generic, these indicators are generic indicators that you can apply and check. Other thing, could be like, I don't know, amount of energy that you have to put for, let's say, training a quantum model versus classical model. Like all of these chat GPT to train them, like so much money and all that is being put. I mean, and the energy is needed. I mean, do you need all that for quantum case? I mean, yeah, like, I mean, so there are these energy challenges. Yeah, like, I mean, noise robustness. Yeah, like somebody just wrote noise robustness is another thing that can be possible. Like, which one is more noise robust? The noise could be adversarial noise or something, like, So yeah, so many of these, like, I mean, indicators, like that one. It very much depends on who is. I mean, if I have lots of money, maybe I care for, like, just accuracy. And let's say if I have all the time in the world, then maybe I don't care about which solves fast. Maybe I solve which solves accurately. Like, so it depends on. Like.
Wonderful. Thank you.
Thanks.
No more question? Oh, okay. From Agung, do you have a plan to build a QML? Oh, do you have a plan to build a QML startup?
I don't think so. Yeah. Yeah.
Okay.
Yeah. Yeah.
Maybe Agung will
idea.
join.
Yeah. Yeah. It's
Okay. There's a follow-up question. Oh, sorry. What feature map kernel should we consider the most? That's from Gagus.
we consider the most. Should we consider the most? Yeah, I think there's some bandwidth issue, and they're like, I don't know. I mean, they are very much like in the heuristic regime. So which one can be useful, which one cannot be. I think people have to try all this. Like, I think I don't know if this can be a problem dependent, and maybe, yeah, you can write a research paper on that. Yeah, for some specific cases and so on. Yeah.
Okay, Gagus raise hand. Okay, please, Gagus, you can ask yourself.
Hello, Kishor.
Yeah, hi, Luis. Yeah.
Yes. Actually, I would like to ask about the quantum machine learning application for quantum chemistry. And I found that we need to include the quantum algorithm like variational quantum eigensolvers. And it's really complicated if we dealing with the molecule with the size, with the large size. So in this case, is we need to optimize the answers, we need to optimize the which one is classical optimizer that we need to use, and also quantum circuit.
Yeah.
So in this case, if we apply the quantum machine learning for the ground state energy of the molecules, so it means that we need to consider so many quantum circuit as a vector map in here, right? So quantum circuit itself is also include the ANSYS insights to get this quantum circuit close to the ground state energy. So in these cases, I still cannot find that for the quantum machine learning is outperform than the classical machine learning for the case of the ground state energy calculation. Because if we dealing with a small molecule, for example, and then we try to calculate using just simple quantum simulator like variational quantum eigensolver, even we found that the computational time is larger than the classical.
I mean, I think it was that I mean, I also don't like, so I came up with new approaches like IQAE and so on, where you don't have this quantum classical feedback loop. So yeah, I mean, I think I can discuss in detail about some of the issue with the NISC, and I think VQE and VQA and like, you know, QA, they are popular, but they have severe limitations. And I personally, you know, like, I mean, I have several concerns with these algorithms. Yeah. I think
Okay, thank you so
much.
much.
That's not the best way. Yeah, I think. Yeah.
Okay, thank you.
I very much echo your sentiment. Yeah, yeah.
Okay, thank you so much.
Yeah.
Thank you. Please, if you have still some question to us. If not, I'm start counting Mississippi 1, Mississippi 2, and Mississippi 3. All right, then let's thanks again to Dr. Kishor Bharti. Thank you again. And I hope this online meeting will be followed up by offline meeting either in Serpong or in Singapore. Hopefully.
I will be very happy to visit and so on. I mean, I have been to Indonesia, I think 2-3 times. Once in Bali, the other time in this place. I mean, near the Komodo Island.
Komodo Island.
Yeah.
Lombok.
Labuan Bajo.
Labuan Bajo.
Okay.
Oh, so beautiful. I think Labuan Bajo is better than Bali. Yeah. Yeah.
Okay, so you've been to Bali, you've been to Labuan Bajo.
Yeah.
Serpong probably next.
Yeah. Very much. Yeah. I will very much look forward to visit there in person, and like with family and so on. Yeah. Okay. Thanks
Wonderful.
a lot. Yeah.
Thanks a lot.
Okay, thank you. Yeah. Bye-bye.
Bye-bye.
Thank you. Bye.
Bye.
Thank you, Kishor.